So coming to the properties of unfolding, I have listed three main properties. First is it preserves the number of delays in a DFG. Sum of delays on the J unfolded edges is same as the number of delays on the edge U to V. So the edge U to V is represented by this equation in the unfolded DFG, and delays number of delays on that edge is calculated by the formula W plus I divided by j, floor function of this for I equal to 0 to j minus 1. Okay, so summation of these delays for I equal to 0 to j minus 1 gives you W. So this can be proved mathematically. Second is that unfolding a DFG with iteration bound results in a j unfolded DFG with iteration bound j infinity. This can be very easily proved. And third is unfolding preserves the precedent constraint of a DSP program. So this is the most important, preserving the precedence constraint. If this is not preserved, then it means that the entire functionality of the DSP program is changed. Then the new DSP program is representing some other program. So two main applications of unfolding are, first is sample period reduction and second is parallel processing. And we are increasing the speed of the system at the cost of increase in area. We are sacrificing area for speed. Okay, so talking about sample period reduction, this can also be done using retiming. Okay, but there are two cases where retiming fails. So first is when there is a node in a DFG that has computation time greater than the iteration bound, and second case is when the iteration bound is not an integer. So in these two cases, the retiming cannot reduce sample period, and hence unfolding is required. So coming to case 1, this is a DFG and computation time of node T is 4 unit time and iteration bound is 3. So in this DFG, two loops are present, loop number 1 and this is loop number 2. So for this loop, the loop bound is 4, 5, 6, 6 by total number of delays in this loop 6 by 2, and for this loop the loop bound is 4, 5, 6, 6 by 3. So this is 2, this is 3, maximum loop bound. So this is iteration bound, and 4, that computation time of node T, that is 4, is greater than iteration bound. Okay, and T sampling for this DFG is 6. This is the critical path, the path with no delay elements. So 4 plus 1 plus 1. So critical path is equal to T sample minimum is 6. Okay, so if you perform retiming on this circuit, so this is the retime DFG. So retiming does not change the iteration bound, so iteration bound will be 3. Now T sampling will be 4. So no matter how much you make the nodes independent, still T sampling minimum will be 4 because the computation time of this node T is 4. So to further increase the sampling rate, we have to perform unfolding. And in this case, the unfolding factor will be ceiling function of Tu by T infinity. So ceiling function of x, suppose x is 1.33. So ceiling function of this 1.33 will give you 2. So ceiling function of x gives the smallest integer greater than equal to x. So if x is 1.33, so the smallest integer greater than 1.33 is 2. Okay, so applying this formula for calculation of unfolding factor j. So tu is 4 and iteration bound is 3, so it is 1.33 and ceiling function will give you 2. So this is a 2 unfolded DFG with iteration bound is 6. So iteration bound will increase j times. 3 into 2 is 6, and t sampling minimum for this circuit is now 3. So this one part of the unfolded version will produce one sample in 6 unit time. So the second part of the unfolded version will produce one sample in 6 unit time. These two samples will be produced parallelly. So the output is two samples in 6 unit time. So sampling period is 6 by 2, that is 3. So the iteration bound is increased, okay, but number of samples produced in the same time is increased. So in that sense, t sampling minimum is 3. So coming to case 2 where iteration bound is not an integer. So for this DFG, the iteration bound is 4 by 3. Okay, so this is a cycle. So adding the computation time of all the nodes, that is 4, and total number of delays is 3. And t sampling minimum will be determined by the critical path time. So this is a critical path with no delay elements in between. So critical path time is 1 plus 1 2, and that is also equal to t sampling minimum, that is 2 for this circuit. So even if you perform retiming or cut set pipelining, means you put two delay elements along this cut set. So one delay element at this point and second delay element at this point. So critical path time will be reduced to 1. But since the iteration bound is 4 by 3, so the iteration period will be 4 by 3. So no matter how much you reduce the critical path time, the iteration period, the lower bound of the iteration period will be determined by iteration bound. Okay, so to increase the sampling rate, now you have to unfold this architecture by a factor j, okay, such that the iteration bound of unfolded DFG is an integer. So j into iteration bound, this will be the iteration bound of this unfolded architecture. This should be an integer. So for j equal to 3, so iteration bound is 4 by 3, and the minimum value of j for which this factor will be an integer is 3. Okay, so for j equal to 3, 3 into 4 by 3 is 4, an integer. So you have to unfold this DFG 3 times. Okay, so the 3 unfolded DFG is given. T iteration is 4. We have calculated that, and based on this calculation we have unfolded it, and t sampling minimum will be 4 by 3, that is j. So you can see that critical path time for this is 3, for this is also 3, and for this is also 3. But even the critical path time is 3, the iteration bound is 4, and the iteration period cannot be reduced beyond this. So this part will produce one sample in 4 unit time. This will also produce one sample in 4 unit time, and this part will also produce one sample in 4 unit time. So altogether we have 3 samples in 4 unit time, and sampling time minimum is 4 by 3. So second main application of unfolding is parallel processing. I have already discussed parallel processing in detail in my previous video lectures. Okay, so our DSP program is given yn is equal to a of xn plus b of xn minus 4 plus c of xn minus 6. So block diagram representation for this is drawn. Okay, so this is the original DSP program. So DSP program or block diagram, these are used interchangeably. So to draw L level parallel structure, you have to follow these steps. You have to first draw the block diagram, or you can say the DSP program. For this, block diagram is shown. Then draw the equivalent DFG. So you have to draw the equivalent DFG for this. So you have to unfold the DFG. So let's say the unfolding factor is 3. So then you have to use the algorithm that was discussed previously to draw the unfolded structure, and then you can draw the equivalent block diagram or DSP program. Okay, so these steps you have to follow. And the sampling rate, suppose the sampling rate of this was k, so the sampling rate of this j times unfolded DSP program will be j into k. If it is generating k samples in a unit time, it will generate j samples in same amount of time. So the sampling rate is increased by factor j into